Hello, welcome. This is SND College of Engineering and Research Center, Yeola. Lecture series for first year engineering. I, Dr. Chaudhary Vivek Sitaram from first year engineering department. So now, today we will see about the quantum tunneling. Now, history of quantum tunneling. The consequences of wave nature of matter, that is from the de Broglie hypothesis. Every moving particle is associated with a wave, and that is nothing but the matter wave. First used to explain alpha decay of heavier elements in 1928 by George Gamow and shown experimentally by Leonard Isaki, that is by tunneling diode. So, force sensors. A UK company is developing flexible force sensors that uses quantum tunneling. These sensors are made out of quantum tunneling composite materials. So, quantum tunneling composite materials is nothing but QTCs. So, QTCs are essential non-conducting in their normal state. When fixed by an applied force, the atoms of the quantum tunneling are brought close enough so that tunneling can occur. Tunneling changes the QTC from an insulator to a conductor with a predictable exponential decay in resistance. Now, here in the graph, if we see, that is when on the x-axis there is a force and on the y-axis there is a resistance. So, in ohm. So, when forces are changing, the resistance will go on decreasing. So, this is nothing but the tunneling effect by sensors. How can be this? So, solution to wave equation have a general form. Now, as in the figure, there is a particle. As shown in the figure, here you can observe that it is having the three parts. Part 1, part 2, part 3. That is portion 1, portion 2 and portion 3. Here portion 1, portion 2, portion 3. So, particle is supposed to pass through the part 2 or portion 2 to the portion 3. Now, this is here we can observe the tunneling effect. Okay. Now, the solution to the wave equations have the general form. In the barrier region, the solution becomes, that is, it can be probability of having the particle in the barrier region also. The wave function decays exponentially in the barrier region. That is, if you observe in this figure, so wave function, if here we consider the psi is the wave function which is varying outside this barrier, normal. Again outside this barrier too, it is normal. But inside the barrier, it is due to tunneling effect, it is decaying exponentially. And if some portion of the wave function still exists on the other side of the barrier, transmission has occurred. And the width of the barrier is the most prominent factor in determining the probability of transmission. That is depending on the width and the presence of the wave function. Now, by using wave packet demonstration, University of Colorado tunneling program. So, you can observe this on now they observe that tunneling and alpha decay. So, George Gamow used the tunneling to explain alpha decay in uranium-238. The alpha particle does not have enough kinetic energy to escape the nucleus. As we know, alpha particle does not have enough kinetic energy to escape the nucleus, as nucleus having the strong forces, so they cannot escape. There is a chance due to its wave function that it will escape the potential barrier of the nucleus boundary. Due to the exponential decay nature of the wave function in the barrier region, the width of the barrier can manifest itself in the half-life of the isotope, and that's why there is a tunneling effect. Due to tunneling effect, we can observe the alpha decay. Now, tunneling and microchip development. As microchip developers create a smaller production processes, we reach the limit of classical computer technology. The feature size of the most advanced microchip today is 45 nanometer. So, as we know, nanometer is nothing but 10 to the power minus 9 meter. So, this is so much a very small scale at the electron level scale. With such a small widths, the electrons in the channel can tunnel out with relative ease, possibly affecting other transistors in the chip. So current approximations show that the minimum feature size is about 4 nanometer. After that, point tunneling is not only possible but highly likely, and chip would fail. So scanning tunneling microscope. So this can be utilized by using scanning tunneling microscope. The scanning tunneling microscope was invented in 1981 by Gerd Beining and Heinrich Rohr. When a metal chip, usually made of tungsten or platinum iridium, is brought within 0.4 to 0.7 nanometer of the sample, electrons tunnel across the gap and create a current in the tip, and through that tip, here you can observe over here. So only through the tip, here the tip of the sensor can sense the distance between these two, and we can observe the scanning of that. This current is then fed to a computer and used to generate an image of the atomic surface of the sample. At the distance of the Coulomb force between the tip and an atom of the sample is actually enough to move the atoms. This has allowed physicists to create images and structures on the atomic level. So in this you can observe. So this can be happen in a tunneling diodes also. We can observe the tunneling effect. So Leona Isaki in 1958 has developed this. So tunneling diodes are designed with a heavily doped PN junction that is only 10 nanometer wide. So here remember the size 10 nanometer wide, and though they are heavily doped, at low voltages the P and N states are aligned, allowing electrons to tunnel across the gap. As voltage increases, these states more misaligned and fewer electrons flow. This negative resistance regions allows the diode to operate at very high frequencies well into the gigahertz range. Here we can observe the negative resistance region. Here from up to this point it is having positive effect, that is PTC, positive temperature coefficient, just like so positive result, just like V is equal to IR can be proved. But from this point to this point, here we are, though the voltage is increasing, current is decreasing, and that's why this region is called as negative differential resistance region. And from this, after this point, again resistance goes on continuously. This negative resistance regions allows the diode to operate at very high frequencies, that is well up to the gigahertz range, and as we know gigahertz range is too much high. So this can also be utilized in a force sensors. Thank you very much.